The morning sun glints off the runway at Hatfield Aerodrome on November 25, 1940, casting long shadows across the tarmac. A peculiar silhouette emerges from the hangars, neither sleek like a fighter nor sturdy like a bomber, but something altogether different. The airframe catches the light in a way no military aircraft should. It gleams, but not with the characteristic sheen of polished aluminium. This machine is built from wood, balsa, spruce, plywood, and birch, bound together with glue and covered in canvas treated with cellulose dope. As the engines turn over and the propellers bite into the cold air, the engineers and designers clustered in the observation post watch with the intensity of men who have staked everything on an impossible idea. They knew that the Air Ministry thought them mad. They knew that their competitors in the fighter program were building machines from the miracle metal that had revolutionized aviation. Yet here, at the threshold between peace and total war, Geoffrey de Havilland and his small team had chosen to build a warplane from materials that belonged in furniture makers' workshops, not on the front line of the Second World War. Within moments, that wooden machine would claw its way into the sky and demonstrate something that would change the course of the air war. Sometimes, the oldest solutions proved to be the most ingenious. By 1940, Britain found itself in a state of desperate material shortage that seemed to rule out the construction of modern fighting aircraft. The German Luftwaffe had achieved air superiority over much of Western Europe, and the British aircraft industry was demanding aluminium alloy at quantities that outstripped the nation's ability to produce it. Aircraft manufacturers competed fiercely for allocations of the precious metal. The Spitfire production program alone consumed vast quantities of aluminium that had been earmarked for other vital aircraft. The situation grew more acute after the German invasion of Norway had cut off supplies from Scandinavian sources. The Air Ministry faced an impossible calculus. How could Britain field fast, modern aircraft when the raw materials that made such machines possible were in critically short supply? Existing bombers were sluggish, vulnerable to German fighters, and suffered catastrophic losses on daylight raids. The Bristol Blenheim, which had seemed a marvel of speed just years earlier, was now regarded as little better than a flying coffin when intercepted by enemy fighters. Night bombing had become the only viable option, yet even these nocturnal sorties incurred losses that Britain could ill afford. What was needed was an aircraft fast enough to evade fighters, armed well enough to strike at targets, yet constructed from materials that would not devour the precious aluminium that was needed for production of Spitfires and other essential types. The requirement seemed to demand the impossible. It was this very impossible demand that fell across Geoffrey de Havilland's desk in the summer of 1938. De Havilland, the founder and chief designer of the de Havilland Aircraft Company, had built his reputation on innovative and unconventional thinking. The Air Ministry issued a specification, a fairly loose one, as was often the case, for a fast, lightly armed reconnaissance and bomber aircraft that would not require extensive use of aluminium alloy. The specification was circulated to the major aircraft manufacturers, and most dismissed it as impractical or simply ignored it. De Havilland and his chief engineer, Ronald Bishop, saw something different. They perceived an opportunity. Bishop, in particular, became convinced that a small, fast, twin-engined aircraft constructed entirely from non-essential materials could be designed with such efficiency that it would outperform larger, heavier machines built in the conventional manner. The concept was audacious. Build an aircraft that was so fast and so maneuverable that it would not need heavy armament. Its defense would be speed itself. The resulting design employed techniques and materials that had their origins in de Havilland's earlier work with experimental and racing aircraft. The Mosquito, as the aircraft became known, was constructed from a wooden monocoque fuselage, the structure derived from processes that aircraft engineers had largely abandoned in favor of metal construction. The fuselage consisted of a complex framework of spruce and birch, covered with multiple layers of birch and mahogany plywood, laminated and glued together with an adhesive called semaindine that had been specially developed for the purpose. The wing structure employed similar construction techniques, with wooden spars and ribs covered in plywood and canvas. The entire surface would be treated with cellulose dope, the same substance used to finish the fabric wings of aircraft from an earlier generation, which would shrink and harden, creating a smooth, airtight surface. 2 Rolls-Royce Merlin engines, the same engines that powered the Spitfire, would drive the machine forward with tremendous force. The manufacturing process represented an entirely different approach to aircraft production, where aluminium aircraft required specialized factories equipped with machinery for riveting, machining, and welding. The Mosquito could be built using techniques familiar to furniture makers and woodworkers. The fuselage was constructed in 2 halves, which were then glued together rather than riveted. This method was considerably faster than conventional riveting and created a smoother surface, which reduced aerodynamic drag. Wing panels were built up from prefabricated sections that could be assembled relatively quickly. The fact that much of the aircraft's structure could be manufactured at furniture makers' workshops and smaller engineering firms meant that production could be distributed across a wide network of suppliers rather than concentrated in a few heavily targeted factories. Halifax's could manufacture sections in their upholstery division. A piano manufacturer named Shackleton contributed production capability. Morris Motors, the automobile manufacturer, built fuselage sections at its Cowley factory. This dispersal of manufacturing, it was hoped, would make the production program resilient to German bombing. The prototype and early production aircraft were built at Hatfield, but the design was engineered from the outset to be built across multiple facilities. The weight of the structure was kept to an absolute minimum through ruthless attention to detail. The Mosquito, with its 2 Merlin engines and all its equipment, weighed roughly 7,000 kilograms, substantially lighter than comparable twin-engined fighters of the period. This extreme lightness, combined with the power of the engines, meant that the aircraft possessed a power-to-weight ratio that was exceptional. To put this in perspective, the structure was so efficient that the ratio of engine power to aircraft weight was comparable to that of a Spitfire, despite the Mosquito being a considerably larger machine. The fuselage length stretched to 12.4 meters, with a wingspan of 16.5 meters, yet the total weight was less than many single-engined fighters. Every kilogram of unnecessary weight was ferreted out and eliminated. The undercarriage was as light as possible whilst remaining robust. The fuel systems were pared down to the essentials. Even the thickness of plywood panels was calculated to the minimum required for structural integrity. The result was an aircraft that promised not only to be fast, but fast in a way that seemed to defy the conventional wisdom of aircraft design. If you are finding this interesting, a quick subscribe helps more than you know. The algorithm rewards it, and it genuinely does help to sustain this channel and allow us to keep producing these deep dives into the machines and innovations that shaped history. The first operational sortie of a Mosquito took place on May 31, 1941, when an aircraft of the de Havilland's test squadron departed from Hatfield on a high-speed reconnaissance mission over occupied France. The pilot, Geoffrey de Havilland, took the machine to Amiens and back, cruising at altitudes above 10,000 meters and speeds approaching 600 kilometers per hour. The success of this flight vindicated everything that de Havilland and his team had claimed for the design. The wooden aircraft was not merely functional, it was demonstrably faster than nearly every fighter aircraft in the Luftwaffe's inventory. German pilots encountered the Mosquito with a mixture of surprise and frustration. The machine was so quick that it could often outdistance enemy fighters that attempted to intercept it. As the war progressed, the Mosquito found itself employed in an ever-widening variety of roles. Fast-day bombers operated from British airfields, carrying bomb loads that were modest by the standards of strategic bombing, but achieved remarkable accuracy due to the aircraft's stability and the capability of its pilots. Night fighters, equipped with radar sets and bristling with machine guns and cannons, hunted German bombers over the skies of Britain. Pathfinders flew ahead of heavy bomber streams, dropping marker flares to guide the main force to their targets. Reconnaissance aircraft flew at speeds that made interception almost impossible. The Mosquito proved adaptable to each role with remarkable ease. The destruction of the Gestapo headquarters in Oslo on November 25, 1942, stands as one of the most audacious Mosquito operations. Norwegian resistance fighters had identified the building as housing crucial records and living quarters for key German security officials. A formation of de Havilland Mosquitoes was dispatched from Britain to strike the target. Flying at low level to avoid radar detection, the aircraft approached from the sea and delivered their bombs with precision that would have been impossible for conventional bombers. The building was destroyed, along with irreplaceable records. The operation was repeated several times against German targets in occupied territory, and each time the Mosquito's combination of speed, maneuverability, and accuracy made such precision strikes possible. In other operations, Mosquitoes engaged in what amounted to individual acts of aerial combat, hunting German fighters and bombers across occupied Europe. The combat record of the Mosquito was remarkable not merely for the number of enemy aircraft destroyed, but for the manner in which the wooden machine could outrun and outmaneuver opponents that had been designed from the outset as fighters. German pilots often reported a sense of helplessness when faced with the Mosquito. The machine would appear on the radar, the pilot would be scrambled to intercept, and by the time the German fighter had climbed to altitude, the Mosquito would be far across the North Sea, heading back towards England. When compared to its German equivalent, the Luftwaffe's answer to the Mosquito was far less successful. The Junkers Ju-88 was a machine of considerable capability, faster in level flight than the early marks of Mosquito, but substantially heavier and requiring considerably more aluminium in its construction. More tellingly, the Ju-88 suffered from chronic structural problems caused by the stresses imposed by its greater weight. Tail flutter and wing divergence were persistent issues that killed test pilots and operational crews. The German aircraft industry was not given the license and frankly possessed neither the infrastructure nor the industrial philosophy to contemplate producing an aircraft primarily from wood. The idea seemed to the German engineering establishment to be a step backwards. The Luftwaffe did eventually design wooden aircraft, but these came late in the war when aluminium shortages became acute, and the designs were rushed and often dangerous. The American equivalent was the North American P-51 Mustang, which combined speed and range with conventional metal construction. The Mustang was a superb fighter and in the long run proved more influential than the Mosquito. However, the Mosquito demonstrated that an entirely different approach to the problem of air superiority was possible. Speed, rather than armor and heavy armament, could be the path to survival in the modern air war. The legacy of the de Havilland Mosquito extended far beyond the Second World War. The aircraft remained in service with the Royal Air Force until 1955, serving in roles from maritime patrol to high-altitude reconnaissance. During the post-war years, as the early jet age blossomed, the Mosquito seemed anachronistic, a propeller-driven machine in the age of turbojet engines. Yet it remained fast enough and reliable enough to retain operational utility in roles that did not demand the range or altitude performance of modern jet aircraft. The design itself influenced later developments in unmanned aircraft and reconnaissance systems. The concept of building high-performance aircraft from non-metallic materials, which had seemed mad in 1940, became central to the design philosophy of modern military aircraft. The composite materials used in contemporary fighters, whilst far more sophisticated than the plywood of the Mosquito, represent an evolution of the same basic principle. Use the lightest and most efficient materials available, rather than defaulting to the material of previous generations. The Mosquito did not win the war single-handedly. No aircraft can claim such a thing. But the aircraft did prove that innovation was possible even under conditions of the most severe material shortage. The machine demonstrated that unconventional thinking about materials and structure could produce results that conventional approaches could never achieve. The final Mosquito aircraft rolled off the production line in 1945, and by that time over 7,400 examples had been built. This production total, remarkable for an aircraft that had been dismissed as impractical by many in the aircraft industry, testifies to the soundness of the design and the efficiency of the distributed manufacturing network that de Havilland had envisioned. The aircraft had been built not only by de Havilland but by Airspeed, Percival, and a host of other manufacturers and component suppliers. A handful of Mosquitoes survive in museums and private collections today. The de Havilland Aircraft Museum at Hatfield preserves an example of the aircraft that first flew from that very aerodrome in November 1940. Standing before the machine, one is struck by its apparent fragility. The wooden structure, now aged and weathered, seems scarcely substantial enough to have carried out the roles that the Mosquito fulfilled.